So welcome back. What we're going to do now is we'll look at the exercise that I set you to do with Ford and Marvin and Arthur. And then I'm going to move on to show you how we can encode the ancestor relation using rules and using recursion. So let's look at the exercise first. So we had three objects in our world. Ford is an alien. He comes from a small planet somewhere in the vicinity of Betelgeuse. Arthur is a human being and Marvin is an android. Those are three actual objects. Then we've got some sets of things. We've got the set of all aliens, and Ford belongs to that. We've got the set of all humans, which has got Arthur in it. We've got the set of all androids, Marvin's in there, and we've also got the set of life forms. And it's going to turn out that Ford and Arthur are in that set. So those are the sets of things. And then we've got one relation, which is to say that someone or something is cleverer than someone else. And eventually we want to infer that Marvin is cleverer than Arthur, because he's got the brain the size of a planet. So when we want to represent the idea that Ford is an alien, or the fact that Ford is an alien, we say alien of Ford. So that's alien is the set of things, Ford is the object which is in that set. So in other words, we say that alien of Ford is true. That goes in our database. Similarly, human Arthur, that's true, and android Marvin. Then we need some rules. The rules say that all humans are life forms. So in other words, if X is a human, X is a life form. Another rule says that if X is an alien, X is a life form. And then the last rule says that androids are cleverer than life forms. So in other words, all androids are cleverer than all life forms. If X is an android and if Y is a life form, then X is cleverer than Y. So that represents our domain. We call it a domain. Basically, it's what we're thinking about. It describes our world, but in such a way that we can now do automated inference. So we're going to try to derive the fact that Marvin is cleverer than Arthur. And the way that we do it is in two stages, because we can't do it straight away, because that rule down there, android X and lifeform Y, implies is cleverer than XY. Well, that Marvin is an android, so that matches against X, but there's nothing in our database that matches with lifeform Y. So we need to derive that first. So the first thing that we do is that we have to derive the fact that Arthur is a life form. So we use the rule human of X implies life form of X. Then then we use the supporting fact human of Arthur. We write down the bindings. That's how the variable matched. Well, human of X has a variable in it here. It's X, and that matches with Arthur. So X has the value Arthur. We then substitute X is equal to Arthur in here into the right hand side of the rule, and we derive the fact that Arthur is a life form. Good stuff. So now we can apply the rule that we want to, which says that if X is an android and Y is a life form, then X is cleverer than Y. So Marvin is an android, Arthur is a life form. We know that from here, so we're allowed to use anything that we've derived already. We needed it from here. So the bindings are that X is Marvin and Y is Arthur. That's that here. And therefore we're allowed to derive the fact is cleverer than XY, with X as Marvin, Y as Arthur. We write it down here and we are done. So now we're going to move on to a different cartoon domain, a nice big family, and it's the Simpsons. This is only part of the Simpsons family tree. If you want to look it up online, the Simpsons family tree is pretty huge. But I've just got a bit of it here. So Bart, Lisa and Maggie are the children, and Homer and Marge are their parents. So that bit here, over this side of the screen, shows you that. Over here, we've got Marge's parents. So Jackie is the parent of Marge, and Clancy is the parent of Marge. In other words, Jackie and Clancy are Marge's mum and dad. And Homer has two parents called Mona and Abe, who I've written here as Grandpa, because that's what they always call him. And we know Grandpa's parents as well. They're called Orville Simpson and Yuma Simpson. That's all that I know of the Simpsons family tree. But what I'd like to know, I could find out here very quickly who Bart's parents are. So I'd say, basically I just look for anything in there. So I could say, if I wanted to ask who are Bart's parents, I'd say, find me the possible fillers for this slot. And it would say Homer and Marge. But I want to actually write down a rule that finds me the ancestors. In other words, it tells me, it allows me to prove that Orville is the parent of Bart. So Orville is the parent of Grandpa, Grandpa is the parent of Homer, and Homer is the parent of Bart. So there's linkages. So it's similar to the train track example that I've been talking about. How can I make that linkage along using rules? And the answer is going to be, as you might expect, related to recursion. How would I actually do it? How would I actually do it if you asked me to do it straight off? Well, what I would do is I would first of all look at who Bart's parents are. Okay, so I'd write down Homer and Marge. So if I'm asked to write a list of Bart's ancestors, I'll scribble it down here. Bart's ancestors. And the first two are going to be Homer, that's his dad, and Marge, that's his mum. But I'm not done yet. What I would then do is I would look to see if I knew who Homer's parents are. And I do. That's Grandpa and Mona. Great. Okay, so now I'll write down Marge's parents and add those. That's Jackie and Clancy. Then I'll see, do I know Grandpa's parents? I do. That's Orville and Yuma. Orville and Yuma. And then that would go on forever if it wasn't for the fact that we don't know any more parents. So I don't know who Mona's parents are. I don't know who Jackie's parents are, Clancy's parents, Orville and Yuma. In the extended tree, I think those are known. But that's all I know. So I know Homer, Marge, Grandpa, Mona, Jackie, Clancy, Orville and Yuma. That's the full list of Bart's ancestors, as far as I know. I want to write down a rule that captures that. So how can I do it? Well, the base case, I'm thinking recursively now, the base case, how can I be an ancestor? Well, one way is to be the parent. So if X is the parent of Y, then X is the ancestor of Y. That's the base case, that's the easy one. But if you tell me, for example, that Y is the ancestor of Z, and that X is the parent of Y, then I know X is the ancestor of Z. Let me say that again. If you know that Y is the ancestor of Z, and you also know that X is the parent of Y, then you can extend the chain one more. You know that X is the ancestor of Z. And that's what we can write down like this. So X is the parent of Y, and Y is the ancestor of Z in some way, then X is the ancestor of Z. And that recursive rule there allows us, I'll go on to that bit in a minute, that recursive rule there allows us to build up as many parent, 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 parent linkages as we need to infer the ancestor linkages. We could also write it like this. If X is the ancestor of Y and Y is the ancestor of Z, then X is the ancestor of Z. That's another way of doing it. So in other words, if you tell me that X is the ancestor of Y, and you also tell me that that Y is the ancestor of Z, then I know that X is the ancestor of Z. Let's take an example. If you tell me that William the Conqueror is the ancestor of Henry VIII, don't know if this is actually true or not, but if you tell me that William the Conqueror is the ancestor of Henry VIII, and I know that Henry VIII is the ancestor of Elizabeth II, don't know if that's true or not either, then I would know that William the Conqueror is the ancestor of Elizabeth II, because I can build the chain that way. So let's see if we can finally do this, show that Orville is the ancestor of Bart. Orville is his great grandfather. So the first thing that we have to do is we have to derive the fact that Homer is the ancestor of Bart, because then we're going to tack another ancestor relation on the front. So the way that we do that is just using the base case. If X is the parent of Y, then X is the ancestor of Y. And Homer is the parent of Bart, so therefore he's his ancestor. Good. Now we'll tack another parent link onto the front of this. We'll use the fact that Homer is the ancestor of Bart. We've got that here. That's going to be this part of the rule. And then we'll use the fact that Grandpa is the parent of Homer to extend the chain one more. And that's what we do here. And then finally, we can do it one more by extending, using the fact that Grandpa is the ancestor of Bart and that Orville is the parent of Grandpa. And then finally, we've got there ancestor Orville Bart. Orville is the ancestor of Bart. So that's using the rules forwards. When we do this in a computer, and if you know anything about Prolog programming language, which you might not, it's very old now, this is the way that it's done. This is the way that it's also done if you're doing automatic theorem proving. And Connor will be showing you, Connor and Jules will be showing you more about this in the second semester. So let's have a look at this. We start from the fact to be proved. Ancestor Orville Bart. How could I prove that using my rules? Well, there's two ways. One way of being an ancestor is to be someone's parent. So is it the case that Orville is the parent of Bart? Well, no, that's not true. So that fails but there's another way in which Orville can be the ancestor of Bart. The way that he can be is that if Orville is the parent of some Y, and that Y is the ancestor of Bart, then it's the case that Orville will be the ancestor of Bart. So we're using the rule, substituting in the values that we do know, Orville and Bart, but leaving blank the values that we don't know. So first of all, we say, okay, parent Orville Y. What do we know about parent Orville? Well, Orville is the parent of Grandpa. So that's one possibility. So let's try that. Let's take Y is Grandpa, put it in here and see if we can make this true. Because if we can make that true, then the whole thing's true. So that's what we do. We substitute it in there and then we try to prove this as what's called a subgoal. So let's try and prove it. One way is that Grandpa is the parent of Bart. That's not true. But the other way is using the rule. Grandpa is the parent of some Y, and that Y is the ancestor of Bart. Well, Grandpa is the parent of Homer. And so now all we need to do is to prove ancestor Homer Bart. One way is for Homer to be Bart's parent, and that's true. So therefore that's true. That means that's true. and therefore the top thing's true. So we've proved the fact by working backwards, and working backwards can often be a good way to go. So finally, I've got an exercise for you to try this week, which involves knowledge engineering and also writing recursive rules. So what I'd like you to do is to translate these into a database of facts and rules. Elmer is an elephant, Larry is a llama, Kermit is a frog. Elephants are bigger than llamas, and llamas are bigger than frogs. Once you've got those, and you've got those rules, I'd like you to try to derive some facts for me, which you should be able to do. Elmer is bigger than Larry, and Larry is bigger than Kermit. Essentially, it's the same sort of thing. If you've got your rules right, both of those will just drop out immediately. But what we can't do at the moment is we've got all this stuff, and you might say, okay, we've got this elephant who's huge, and the llama who's middle-sized, and the frog that's small. I should be able to derive the fact that Elmer is bigger than Kermit. But I can't actually do that at the moment. I've got no rule. Now, you could put in a rule that just says that elephants are bigger than frogs. But in fact, that's kind of wasteful, because then you end up putting in a thing that says elephants are bigger than ants, and elephants are bigger than budgerigars, and elephants are bigger than walruses. I don't know. What we'd like is a nice general purpose rule that allows us to derive the fact that Elmer is bigger than Kermit. So see if you can find that. And I look forward to seeing your answers.